Sample problem 3.7. The welded tubular frame, okay, that's a tubular frame, is secured to the horizontal XY plane by the ball and socket joint at A and receives support from the loose fitting ring at B. Okay, B is along the Y-axis. Okay. Under the action of the 2 kilonewton load, rotation about a line from A to B is prevented by the cable CD, and the frame is stable in the position shown. Neglect the weight of the frame compared with the applied load and determine the tension T in the cable, the reaction at the ring B, and the reaction components at A. Okay, so step 1, free body diagram. Replace the cable with the tension T. We have the force F equals to 2 kilonewton. We replace the ball and socket with reaction forces in the X, Y, and Z. And we replace this with simply a force in the X and the Z. Why no force in the Y direction? Because this support doesn't resist motion in the in the Y direction. That's all that support. That's all we do when we draw a free body diagram. Is we take away that support and we replace it with forces that it could potentially apply to the structure. Very good. Okay, 1 mark there, or 2 marks. Now we know that our general way of solving these problems of equilibrium is we have these equations, sum of the moments equal to 0 and sum of the forces equal to 0. Now the way that we would often take is we would say, okay, well, how about we take point A here and we say sum of the moments about A equals 0, and then what would happen was these 3 forces would cause no moments because they pass through the point of rotation, but then we would have F, T, and Bx and By as in our equation, in this equation, right? And we would have 1 unknown, 2 unknowns, and T. So we would have 3 unknowns in one equation. Well, they show a slightly advanced trick, okay, which is how can we take moments about something so that we eliminate as many unknowns as possible. And this is to take moments about a line, an axis, that passes through that point A and that point B. So if we take moments about that axis, then we are eliminating Bx, By, Bz, Bx, and the 3 A forces. Does that make sense? So we want to now take moments about this axis. So the first thing we need to do is we need to get the unit vector for this axis. Okay? And I'm not going to go into the details there, but that is the unit vector. Well, there it is. Remember that a unit vector is simply R AB in vector form divided by the magnitude of RAB. What is a position vector? It is how do I go from that point to that point in XYZ space. I go, as you can see, there's no X component, so all I do is I go 4.5 in the Y direction, 4.5 in the Y direction, and then I go 6 in the Z direction. That's what we get there, 4.5 plus 6. That's this thing here. And then we divide by the magnitude, 6 squared plus 4.5. And we get that. That is our unit vector in this direction. And we'll see how we will use it in a second. Okay? And I'm going to refer to something on page 76 which you need to go and have a look at. Okay, so guys, instead of taking moments about A or moments about a point B, we are now taking moments about an axis. Okay? So All unknowns except t may be eliminated by a moment sum about the line AB. So put this into your bag of tricks. Yes, if you did it about A or B, you could get the right answer, but let's try to eliminate all those, and then we can calculate t in our moment equation. Then the next step, which I'm not going to go through in detail, is we now calculate t, but we first need to convert that t into vector form. So how do we do that? Well, remember, we need to multiply t, this is just a little magnitude there, by a unit vector from that point to that point. Okay, a unit vector from that point to that point, from C to D. So calculate unit vector CD. Alright, I don't know where they've put it here, but this is it here. That is your unit vector CD. I'm going to call it NCD. And you multiply that unit vector with t. And then you've converted it into the t vector, the tension vector. Because remember, if we're summing moments, it's R cross F. And these are all vectors. Okay? Alright, so you guys happy with that? Now we've got t in vector form. We need to convert F into vector form. And so F is just 2 kilonewton, but it's going in the positive y direction, so 2J. So we've converted both these forces, tension and force, into vectors. And now we're going to take their moments about this line. Okay? So now, how are we going to do this? Well, we're going to do this. Okay, what is this? This is, there you can see, we're taking moments, R cross a force, and what's actually happening here is we're taking moments about point A. Then you say, but you just told me we're going to take moments about this line. Okay, that's fine. We first take moments about point A, and then we get the component of that moment about that axis there. And that's where the dot n comes in. So we say, we take moments about point A, which means we need an R and an F. What is our position vector? It's any vector from point A to any point along the line of action of t. And so you can either choose AD or AC. Remember, that's a C there. So that position vector AD, okay, is a position vector from A to any point along the line of action of t. Okay, so we've got that, and we cross it with t, and now we've calculated the moment of t about point A. But then, okay, but I thought you said we're going to calculate around the axis. Well, that's why we dot. Now we've got a vector, we've got our moment, but we dot it with n to get the component. You see there's R1 cross t. Now we dot it with n, with this guy, and then we get the component of the moment acting about line AB. Does that make sense? Are you happy with that? So the sum of the moments about line AB equal to 0. We've got our R1. Make sure that you can understand where that comes from. R1, that's R1. Cross T. Here's T. But then we have to dot it with our unit vector AB. And then again, we also do that for this force. Right? We're calculating the moment of this force about that line. So we need a position vector from A to any point along the line of action. So the only one that we can find here is that point and that point. We calculate our position vector. Make sure that you can get this. There's our position vector R2. There's R1 and R2. There's R2. And we say R2 cross F. Okay, that gives us our moment of that force about point A. But now we need to dot it with the unit vector AB. And we set that equal to 0. So we've taken the sum of the moments about that AB axis. Okay? Then we can solve for T. Okay? So we're the only unknown that we have. Remember, we've got a vector here that gives us a moment, and that gives us a moment. These are two vectors. That's a vector, and that's a vector. Right, there's a cross and a cross, so you get a moment of T about A, and this is the moment of F about A, and so you've got, let's call it M1 there, and you've got an M2, and they're both vectors, and then you're dotting two vectors. You're dotting two vectors to get a scalar. You're dotting two vectors to get a scalar. So you end up with a scalar. Okay? That's what we have, and we can solve for T, 2.83 kilonewton. Now, because we've got the components, we can then go ahead and calculate. Well, we just multiply, we put T over there, divided by the square root of 46.2, and multiply it in. And we can get our three components of T. Tx, Ty, and Tz. Does that make sense? And then, once we've got that, now we've got T, now we can go ahead and we can calculate the rest of the moments, okay, using some of the moments about the z-axis, about the x-axis, and then the three equations of equilibrium for the forces. Okay, I'm not going to go into that. I think I've done the heavy lifting here. You can just go through this and make sure that you get it. Okay? All right.